Welcome my friends. In this video, we will solve trigonometric equations using the double and half angle identities. I have all of the double and half angle identities on the screen now, and we will use these identities to solve trigonometric equations throughout the rest of this video. Let's try this problem. We are asked to find all solutions to the equation negative sine of x plus cosine of 2x is equal to 1 on the interval of 0 to 2 pi. For this problem, we notice that we have cosine of 2x, or cosine of a double angle. There are actually three different identities related to cosine of 2x. We would like to choose the option that converts cosine to sine, since we already have a sine in our problem. The option is cosine of 2x is equal to 1 minus 2 sine squared of x. So we can substitute 1 minus 2 sine squared of x for cosine of 2x in our problem. We get negative sine of x plus 1 minus 2 sine squared of x is equal to 1. We would like to get everything onto one side of the equation, so let's subtract 1 from both sides. The 1's will cancel on both sides of the equation, and we will be left with negative 2 sine squared of x minus sine of x is equal to 0. I've written the negative 2 sine squared of x first, and the negative sine of x second. We have a sine of x in common between our two terms, so we can factor out a sine of x. We will have sine of x times negative 2 sine of x minus 1. We can verify that we factored correctly because sine of x times negative 2 sine of x is negative 2 sine squared of x, and sine of x times negative 1 is equal to negative sine of x. By the zero product property, we can split this into two problems. We have sine of x is equal to 0, and negative 2 sine of x minus 1 is equal to 0. We know that sine is equal to 0 twice on one revolution of the circle. Once at 0, and another time at pi. So our two solutions related to this equation are x is equal to 0 and x is equal to pi. Let's solve the second equation. If we add 1 to both sides, we will get that negative 2 sine of x is equal to 1. If we divide both sides by negative 2, we get that sine of x is equal to negative 1/2. Sine of x is equal to negative 1/2 twice on one revolution of the circle. Sine is negative in either quadrant 3 or quadrant 4. We know that sine of pi over 6 is equal to positive 1/2, so we need the angles for which pi over 6 is the reference angle in either quadrant 3 or quadrant 4. In quadrant 3, we would have 7 pi over 6. 7 pi over 6 is in quadrant 3, and sine of 7 pi over 6 is negative 1/2. The other option will be 11 pi over 6. This is the angle in quadrant 4. Sine of 11 pi over 6 is also equal to negative 1/2. So altogether, we have four different solutions to this equation: x equals 0, x equals pi, x equals 7 pi over 6, and x equals 11 pi over 6. Let's try another problem. We are asked to find all solutions to the equation the square root of 3 times the sine of x plus 2 times the sine of 2x is equal to 0. Notice that we are asked to find all solutions and not just the solutions on one revolution of the circle. The first thing I notice is that I have sine of 2x, or sine of a double angle. There is only one double angle formula related to sine, and it is that sine of 2x is equal to 2 times the sine of x times the cosine of x. So let's replace sine of 2x with 2 sine of x cosine of x in our problem. This is what we have. At this stage, both of our terms have a sine of x in common, so we can factor out a sine of x. We will be left with square root of 3 plus 2 times the cosine of x in parentheses. We can verify that we factored correctly because sine of x times the square root of 3 is equal to square root of 3 sine of x, and sine of x times 2 cosine of x is equal to 2 sine of x cosine of x. By the zero product property, we know that either sine of x is equal to 0 or the square root of 3 plus 2 times the cosine of x is equal to 0. Sine of x is equal to 0 on two places on one revolution of the circle, either at 0 or at pi. In this problem, we are asked to find all solutions. So we can have 0, or pi, or 2 pi, or 3 pi, or 4 pi, or 5 pi, or in general, x equals k times pi, where k is some integer. As for the second equation, we can subtract square root 3 from both sides. We'll have 2 times the cosine of x is equal to negative square root 3. Dividing both sides by 2, we will get that cosine of x is equal to negative square root 3 over 2. Cosine of x is equal to negative square root 3 over 2 twice on one revolution of the circle. We know that cosine of pi over 6 is equal to positive square root 3 over 2. we need negative square root 3 over 2, and cosine is negative in either quadrant 2 or quadrant 3. So we need the two angles that have a reference angle of pi over 6, either in quadrant 2 or quadrant 3. In quadrant 2, the angle is 5 pi over 6. Cosine of 5 pi over 6 is equal to negative square root 3 over 2. We also have any angle that is coterminal with 5 pi over 6. So if we just add or subtract 2 pi some integer number of times, we will get a coterminal angle that will also be a solution. The way we represent this is 5 pi over 6 plus 2k pi, where k is an integer. The other time on one revolution of the circle, where cosine is negative square root 3 over 2, would be in quadrant 3. The relevant angle is 7 pi over 6. So we also have the solution of x equaling 7 pi over 6 plus 2k pi, where again k is an integer. Let's try one final problem. We are asked to find all solutions to the equation 2 minus 2 times sine squared of x is equal to 2 cosine squared of x over 2. In this problem, we have a half angle. We have x over 2. We know that the half angle formula related to cosine is that cosine of x over 2 is equal to plus or minus the square root of 1 plus cosine of x divided by 2. But we don't have cosine of x over 2, we have cosine squared of x over 2. So let's square both sides of this formula. We will get cosine squared of x over 2 is equal to 1 plus cosine of x divided by 2, since squaring cancels the square root. Because it doesn't matter if the original result was either positive or negative. Either way, when we square it, we will get a positive answer. So let's substitute this into our problem. We have 2 minus 2 sine squared of x is equal to 2 times cosine squared of x over 2, which is just 1 plus cosine of x over 2. The 2's will cancel, and we will be left with 2 minus 2 sine squared of x is equal to 1 plus cosine of x. We want to get everything in terms of either sine or cosine. Since we have a squared trig function on the left-hand side in sine squared of x, we can convert this to cosine squared of x using a Pythagorean identity. We know that sine squared of x is equal to 1 minus cosine squared of x. I always remember that 1 minus either sine squared or cosine squared always gives you the other one. So in this case, 1 minus cosine squared is the same thing as sine squared. So let's replace sine squared with 1 minus cosine squared in our problem. We have 2 minus 2 times 1 minus cosine squared is equal to 1 plus cosine of x. Make sure you use parentheses, because 2 must multiply the entire quantity of sine squared, which is 1 minus cosine squared. Distributing the 2, we get 2 minus 2 times 1, which is minus 2, plus 2 cosine squared of x, since negative 2 times negative cosine squared of x is equal to positive 2 cosine squared of x, is equal to 1 plus cosine of x. The 2's over here cancel, and we are left with 2 cosine squared of x is equal to 1 plus cosine of x. Let's get everything to one side of the equation. If we subtract 1 and cosine of x from the right and left-hand side, we will be left with 2 cosine squared of x minus cosine of x minus 1 is equal to 0. Now we can factor this thing. We need to find two values that add to our b term, which is negative 1, and multiply to our a times c term, which is 2 times negative 1, or negative 2. The two values are negative 2 and positive 1. Negative 2 times positive 1 is equal to negative 2, and negative 2 plus 1 is equal to negative 1. If you have a value for a multiplying your squared term when you're factoring, you must divide by that value to find your solution in the chart. So let's divide both sides of the chart by positive 2. Let's simplify. Negative 2 over 2 is the same thing as negative 1 over 1, and 1 over 2 can't be simplified. Always write your simplified form as a fraction, even if it is over 1. From here, we know that we can read from bottom to top. The bottom relates to the variable, in this case cosine, and the top refers to the constant. So we have cosine of x minus 1 for our first factor, and 2 cosine of x plus 1 for our second factor. By the zero product property, we know that either cosine of x minus 1 must be equal to 0, or 2 times the cosine of x plus 1 must be equal to 0. Solving the first equation, if we add 1 to both sides, we get that cosine of x is equal to 1. Cosine of x is equal to 1 only one time on one revolution of the circle. It's when cosine is equal to 0. Since we need to find all solutions, we could have any angle that is coterminal with 0. The way that we write this is that x is equal to 2k pi, where k is any integer. So we could have 0, or 2 pi, or 4 pi, or negative 2 pi, or negative 4 pi, or in general, any multiple of 2k pi, where k is some integer. For the second equation, if we subtract 1 from both sides, we get 2 cosine of x is equal to negative 1. Dividing both sides by 2, we get that cosine of x is equal to negative 1/2. Where is cosine of x equal to negative 1/2? Well, there are two different places on one revolution of the circle. Cosine is equal to positive 1/2 when the angle is pi over 3. So we need angles that have a reference angle of pi over 3 where cosine is negative, which would be either in quadrant 2 or quadrant 3. The angle in quadrant 2 will be 2 pi over 3. But of course we need all solutions, so we could have any angle that is coterminal with 2 pi over 3, so we must add 2k pi, where k is some integer. The other solution would be in quadrant 3. The angle coterminal with pi over 3 in quadrant 3 would be 4 pi over 3, so 4 pi over 3 is also a solution. Of course, since we need all solutions, we will have 4 pi over 3 plus 2k pi, again where k is some integer. Alright my friends, that finishes this video using the double and half angle identities to solve trigonometric equations.